Hello all, welcome to the class of Calculus and Differential Equations 21 MAT 11. Today, I am going to teach a topic in Module 2, Differential Calculus 2. And the topic that I am going to discuss is about partial differentiation basics and Jacobians. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Let us first know the definition for partial differentiation. Partial differentiation. The process of finding partial derivatives is called partial differentiation. The process of finding the partial derivatives is called partial differentiation. So we do partial differentiation. Suppose I consider an example that u is a function of x and y. Then the first order partial derivatives are given by dou u by dou x, dou u by dou y. Similarly, the second order partial derivatives are denoted by dou square u by dou x, dou y, dou square u by dou x square, dou square u by dou y square. So these are the partial derivatives that we can write u as a function of x and y. So to make better understand, I'll just give a simple example first, just to understand the partial differentiation concept. Suppose I want to differentiate with respect to x partially the function x square y cube. So with respect to x, when we want to differentiate, we treat the variable y as constant. So this will be y cube constant, writing as it is. We differentiate partially only x square term. So this gives us y cube into 2x. Differentiation of x square is 2x. The same function, if I want to differentiate partially with respect to y, then x is treated as constant. We write down x square term as it is. Differentiation with respect to y partially for y cube gives us 3y square. So this is how the partial differentiation concept is taken care of. Now we will understand Jacobians. Jacobians. Suppose u is a function of two independent variables x and y. We write down two functions, dependent functions, say u and v. So let u and v be functions of two independent variables, x and y. Then the Jacobian, usually denoted by capital J, of u and v with respect to x and y. Then the Jacobian J of u and v with respect to x and y is defined as J of uv with respect to xy, which is one and the same as writing dou uv with respect to xy. And this is obtained by expanding the 2 cross 2 determinant, 2 cross 2 determinant, dou u by dou x, dou u by dou y in the first row, dou v by dou x, dou v by dou y in the second row. It is two dependent variables u and v with respect to two independent variables x and y. So it is a 2 cross 2 determinant. First row u with respect to x, y. Second row v with respect to x and y. Now this is with respect to two dependent variables and two independent variables. Next we will define u, v, w with respect to three independent variables x, y, z. If u, v, w are functions of three independent variables, x, y, z, then the Jacobian J is defined as J of u, v, w with respect to x, y, z. Alternate notation dou u, v, w with respect to x, y, z. So it is three dependent variables with respect to three independent variables. So this will be a 3 cross 3 determinant expansion. So first row, dou u by dou x, dou u by dou y, dou u by dou z. Second row, dou v by dou x, dou v by dou y, dou v by dou z. Third row, dou w by dou x, dou w by dou y, dou w by dou z. So this will, on expansion of the determinant 3 cross 3, we'll be able to obtain the Jacobian of u, v, w with respect to x, y, z. Now we will do problems on Jacobians. Problems. First one, if u is equal to x plus 3y square minus z cube, v is equal to 4x square yz, and w is equal to 2z square minus xy, then evaluate dou of UVW with respect to XYZ, that is Jacobian, at the point 1, minus 1, 0. We need to obtain the Jacobian of UVW with respect to XYZ at the given point, that is 1, minus 1 and 0. Given the function UVW, first we will find out the partial derivatives with respect to x, y, z respectively, then substitute in the formula for Jacobian and evaluate at the given point. Solution. So it is given u is equal to x plus 3y square minus z cube. So let us find out dou u by dou x. With respect to x, when we differentiate partially, y and z are constants, so 3y square differentiation goes to 0, z cube differentiation with respect to x goes to 0. Differentiation of x with respect to x partially is 1. Dou u by dou y, the first term and the last term are constant, that is x is a constant, z cube is a constant with respect to y. So differentiation of 3y square is 6y. Then we have dou u by dou z. With respect to z, when we want to differentiate partially, both x and y are constants. So differentiation of x with respect to z is 0. 3y square differentiation also goes to 0. Differentiation of minus z cube is minus 3z square. In the same way, we consider the function v given as 4x square yz. So dou v by dou x, we are differentiating partially with respect to x. With respect to x, 4yz is a constant. 4yz is a constant. We'll write in the product, we will write 4yz as it is. Differentiation of x square partially with respect to x gives us 2x. So this is equal to 8xyz. Next we have dou v by dou y. When we differentiate partially with respect to y, 4x square z are constant. We will write them as it is. y differentiation with respect to y is 1. So we get 4x square z. Then we have dou v by dou z. With respect to z, 4x square, y is a constant. Differentiation of z partially with respect to z is 1. So we get 4x square y. Now we will consider the function w, which is given by 2z square minus x into y. 2z square minus x into y. So dou w by dou x. With respect to x, the first term 2z square is constant, so differentiation goes to 0, minus y into 1. X differentiation with respect to x is 1, so minus y into 1 gives us minus y. Dou w by dou y. With respect to y, again 2z square is a constant, so differentiation goes to 0, minus x into 1, which gives us minus x. Then dou w by dou z is equal to differentiation of 2z square is 4z. X and y both are constant, so differentiation partially with respect to z goes to 0. So these are the partial derivatives obtained. Now we will write down the formula for Jacobian. So Jacobian J is equal to dou of UVW with respect to XYZ. And this is given by 3 cross 3 determinant dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou y, dou v by dou z, dou w by dou x, dou w by dou y, dou w by dou z. And this is a 3 cross 3 determinant. We will substitute all the respective partial derivatives what we obtained just now. So dou u by dou x, dou u by dou y, dou u by dou z, which gives us 1, 6y minus 3z square. Second row, 8xyz, 4x square z, 4x square y. And the third row, minus y, minus x, 4z. Now we do not evaluate this 3 cross 3 determinant directly. At the given point, we will evaluate it. At the point 1, minus 1, 0. So Jacobian J will be, wherever x is there, substitute x as 1, substitute the value of y as minus 1 and z is equal to 0. And then we can rewrite the determinant. So we have 1. When y is 0, this becomes minus 6. Z is 0, so last term in the first row goes to 0. Z is 0, Z 0. And then we have 4x square y. Y is negative, so we get minus 4. Last row it will be 1, minus 1, 0. Now we need to expand this 3 cross 3 determinant. So on expansion of the determinant, we will be obtaining J is equal to 1 into 0 minus 4 plus 6 into 0 plus 4, and the last term is 0 multiplied by anything will give us 0 itself. So we have minus 4 plus 6 into 4 is 24. So the required Jacobian at the given point is 20. I'll just explain the expansion of this 3 cross 3 determinant for you. So 1 into, we'll leave the first row and the first column, and it's a product of 0 into 0 minus of minus 4 into minus 1, which gives us the first term here. Then we have minus of minus 6. When we expand the determinant, we take care, we assign plus, minus, plus. So middle term should give you minus. Minus of minus 6 gives me plus 6 multiplied by 0 into 0 is 0. Minus of minus 4, which gives me plus 4. And lastly, the third term is 0. 0 multiplied with 2 cross 2 determinant will give you 0 itself. So that is how we have evaluated the Jacobian. So if we simply know the partial differentiation concept and the Jacobian formula is memorized, this is finding out the Jacobian at the given point. Now we'll do another problem on Jacobian. Second question. If u is equal to xy divided by z, v is equal to yz divided by x, w is equal to zx divided by y, then evaluate Jacobian of UVW with respect to XYZ evaluate Jacobian of UVW with respect to XYZ. So let us take up this problem. Procedure remains the same as we did in the previous case. We consider these functions given, u as a function of xyz, v and w also as a function of xyz, and find out the partial derivatives, u with respect to xyz, v with respect to xyz, and w with respect to xyz first. Then we will use it in the Jacobian formula. Solution. So let us consider first u. u is equal to xy divided by z. Let's find the partial derivatives, dou u by dou x. With respect to x, y and z are constants, writing down as it is. Differentiation of x with respect to x is 1. Then similarly, dou u by dou y. With respect to y, x by z is a constant. Differentiation of y with respect to y is 1. Dou u by dou z. With respect to z, xy is a constant. Differentiation of 1 by z we have. When we are differentiating with respect to z, x into y is a constant, we write it as it is. Differentiation of 1 by z gives us minus 1 by z square. So this gives me the answer as minus xy divided by z square. Similarly, when we consider the function v, which is yz divided by x, we have the partial derivatives. Dou v by dou x is equal to minus yz divided by x square. Dou v by dou y is equal to z by x. Dou v by dou z is equal to y by x. Let me just explain how this is. Considering the function v is equal to yz divided by x. With respect to x, when we want to differentiate partially, yz is a constant, we write it as it is. Differentiation of 1 by x is minus 1 by x square. With respect to y, when we want to differentiate, z by x is a constant. Differentiation of y with respect to y is 1. And with respect to z, when we want to differentiate, y by x is a constant. Differentiation of z in the numerator with respect to z is 1. Now we consider w, which is zx divided by y. So we find the partial derivatives, dou w by dou x, z by y, dou w by dou y minus zx divided by y square, dou w by, we have the third one, dou w by dou z is equal to x by y. So it was in the same manner how we did the previous partial derivatives. With respect to x, z by y is a constant. Differentiation of x with respect to x partially is 1. With respect to y, zx is a constant. Write it down as it is. Differentiation of 1 by y is minus 1 by y square. And with respect to z, finally, x by y is a constant. Writing as it is. Z differentiation gives us 1. So with all these partial derivatives, we are going to substitute in the Jacobian formula. So Jacobian J is equal to dou of UVW with respect to XYZ. And this is a 3 cross 3 determinant. We'll write on the formula first. Dou U by dou X, dou U by dou Y, dou U by dou Z, dou V by dou X, dou V by dou Y, dou v by dou z, and the third row dou w by dou x, dou w by dou y, dou w by dou z under 3 cross 3 determinant. Now we will substitute the partial derivatives. I expand the determinant later. So this is in turn is equal to first row y by z, x by z minus xy divided by z square. Second row minus yz divided by x square, z by x, y by x. Third row z by y minus zx divided by y square and x by y under 3 cross 3 determinant. Now we need to expand this 3 cross 3 determinant. There are two ways of proceeding further. Either you can take what is common entirely in the first row, second row and third row and take it as a product outside the determinant, or you can directly expand the determinant. So I'll be taking what is common. So we observe in the first row, taking LCM kind of, I can take z square common in the denominator so that each of the first and the second term should be multiplied by z. Second row, I can take 1 by x square common so that the second and the third term will be multiplied to the numerator by x. Third row, we will take 1 by y square common so that we remain first and the third term to be multiplied by y in the numerator. So following the same steps, I have 1 divided by Jacobian j is equal to 1 divided by x square, y square, z square common. And now under 3 cross 3 determinant, first row we should multiply by z for the first and second term. So yz, xz minus xy, yz, xz minus xy. Similarly, second row, when I take 1 by x square common, minus yz, zx, yx. We have minus yz, xz, xy. Same way, when in the third row we take 1 by y square common, this will be multiplied by y in the numerator. So yz minus xz, xy. So we have yz minus xz and this is xy. Now we will expand the determinant. So yz multiplied by, we have product of these terms, xz into xy minus of xy into minus xz. So this product gives me x square yz minus of minus plus x square yz. X square yz plus x square yz. We already have a minus sign in this product. While expanding this determinant 2 cross 2, we get another minus sign. That is why it becomes plus. The middle term has minus xz multiplied by minus yz into xy. So that gives us minus x y square z minus x y square z, and product this again xy into yz. Xy into yz again gives us xy square z, and while expanding determinant there is a minus sign, so minus xy square z, and the last term is plus of minus xy multiplied by this minus xy I wrote as it is. Then we have minus yz into minus xz, so which gives us positive xyz square minus xyz square. This gives us xyz square. This is minus into minus plus xyz square. So this is minus xyz square. This is getting cancelled. So last term xyz square is getting cancelled. The previous two we have to add up. 1 divided by x square, y square, z square. Yz multiplied with 2x square yz. Minus of minus, each of these term has minus sign common. So I'm taking minus of minus becomes plus. X y square z, x y square z. They are getting added because both are minus sign. So minus of minus common. So 2xz multiplied by 2xy square z. So Jacobian is equal to 1 divided by x square y square z square multiplied by 2x square y square z square plus 2x square y square z square. So this gives us 1 divided by x square y square z square multiplied by 4x square y square z square. So the product x square y square z square get cancelled, and hence the Jacobian value is 4. So this is how we work out problems in Jacobian. This was also a direct question for us. We just had the fractional term in UVW. So carefully we need to partially differentiate with respect to x, y, z and then expand the Jacobian. Taking out 1 divided by x square y square z square common is not a compulsion. In each row, I took what is common in the denominator as a common term outside the determinant to make the determinant simplification easier. That's all. Now we will take up the third problem. If x plus y plus z is equal to u, y plus z is equal to uv, z is equal to uvw, then evaluate dou of x, y, z with respect to uvw. We need to obtain the reverse of the Jacobian. It's actually means first we have to represent x, y, z in terms of uvw. We have to express x, y, z in terms of uvw first, and then use a formula for Jacobian in the reverse way. That is Jacobian of x, y, z with respect to uvw we have to define. So let us take up the solution. First, let us consider the given expression for u, uv and uvw and try to simplify and obtain x, y, z representations with respect to uvw. So it is given that x plus y plus z is equal to u. But from the second one, y plus z is equal to uv is given. So therefore, I can use y plus z in the previous expression as uv, and that gives us x is equal to u minus uv. So if you observe, we represented x in terms of uvw. Of course, w is not involved here, but still x is represented in terms of uv. And now we will try to represent y plus z is equal to uv we have. Let us substitute for z as uvw from the last expression and try to represent y also with respect to uvw variables. Now, y plus z is equal to uv, but z is equal to uvw. So therefore, y plus uvw is equal to uv, or we have y is equal to uv minus uvw. So we now represented y also with respect to uvw. And lastly, z, if we observe, z is already represented in terms of uvw. So I'll just directly write out that z is directly given as uvw. So these are the three expressions for x, y, z for us. In order to obtain the partial derivatives, dou x by dou u, dou x by dou v, dou x by dou w. Similarly, dou y by dou u, dou y by dou v, and dou y by dou w. Dou z by dou u, dou z by dou v, and dou z by dou w. So let us find all those partial derivatives and then use the formula for Jacobian of x, y, z with respect to u, v, w. Now we consider one by one expressions what we obtained just now. So consider x is equal to u minus uv. So we have to find out the partial derivatives dou x by dou u. With respect to u, we have to differentiate partially. So this gives us 1 minus v. X we have to differentiate partially with respect to u. So with respect to u differentiation is 1 minus v is a constant, writing down as it is. U with respect to u is 1. So we get 1 minus v. Similarly, dou x by dou v we have to find out. It is 0 minus u, which is minus u. Dou x by dou w will be 0 because both u and v are constants. With respect to w, when you want to differentiate, both u and v terms are constants, so differentiation goes to 0. Similarly, we now consider y. We obtain the expression for y as uv minus uvw. Now let us differentiate partially with respect to uvw. So dou y by dou u is equal to v minus vw. Dou y by dou v is equal to u minus uw. Dou y by dou w is equal to minus uv. Let me explain these partial derivatives to you. Y with respect to u, when I differentiate, v is a constant, writing down v as it is, minus v into 1. Differentiation of u with respect to u is 1. So v minus vw is a constant, writing down vw as it is. Differentiation of u gives you 1. So v minus vw. Similarly, dou y by dou v. With respect to v, u is a constant, write it as it is. Differentiation of v with respect to v is 1. Minus uw is a constant, writing as it is. Differentiation of v with respect to v is 1. Now dou y by dou w. With respect to w, uv are constant. So differentiation of the first term goes to 0. Minus, with respect to w, we have minus uv. Minus uv term. Now we will consider the last expression, that is for z. Z is given by uvw. So let us find the partial derivatives. Dou z by dou u is vw. Dou z by dou v is uw. Dou z by dou w is equal to uv. With respect to u, vw are constants. U differentiation is 1. With respect to v, uw are constants. V differentiation is 1. With respect to w, uv are constants. Differentiation of w with respect to w is 1. Now with all these, we will substitute in the formula for Jacobian. So therefore, J is equal to Jacobian of xyz. We are finding xyz with respect to uvw. And the formula is dou x by dou u, dou x by dou v, dou x by dou w in the first row, dou y by dou u, dou y by dou v, dou y by dou w in the second row. Third row, dou z by dou u, dou z by dou v, and dou z by dou w. This is under 3 cross 3 determinant. Now let us expand this 3 cross 3 determinant, and before expanding, of course, we need to substitute the values that we obtained. 1 minus v minus u 0, v minus vw, u minus uw, minus UV, VW, UW, UV. So we will expand this 3 cross 3 determinant. First 1 minus V is multiplied with product of this 2 cross 2 determinant leaving that particular row and that particular column. So U minus UW into UV minus of minus UV into UW. That is how we get the first term. So we have U minus UW into UV minus of minus plus U square VW. The middle term has minus U. When we expand the determinant, there is a minus sign assigned for the middle term of that 3 cross 3 determinant. So this gives us plus U into, leaving that second column and the first row. We will get minus of minus plus U is multiplied by V minus VW into UV minus of minus UV into VW. V minus VW into UV minus of minus plus UV square W. So this gives us 1 minus V multiplied by, let us multiply the terms, U square V minus U square VW plus U square VW. These two get cancelled, plus U into UV square minus UV square W plus UV square W. So again these two get cancelled. So we have Jacobian J is equal to 1 minus V multiplied by U square V plus U multiplied by UV square. So this gives us U square V minus U square V square plus U square V square. So finally, Jacobian is U square V. We have to just carefully simplify this 3 cross 3 determinant, and if there is like terms with one positive and negative, we have cancelled them, and this is how we are getting the Jacobian for this particular problem, that is Jacobian of XYZ with respect to UVW. Hope the problems on Jacobians are helpful. Thank you for watching.